In order to introduce next speaker, I give the word to my colleague, to Anton Svetlichny. Anton, please. Can you hear us, Anton?
Yes, I can hear you. Just want to check if Carrie, can you unmute yourself? Do you have the right? Oh, yeah, amazing. So, thank you, Andrei. I'm happy to introduce to you our next lecturer, Dr. Carrie Weidner. She did her PhD in GILM at the University of Colorado Boulder, where she invented the new method of inertial sensing using cold atoms called Shaken-Lattice interferometry. After that, she moved to Aarhus University in Denmark to work on quantum simulation using quantum gas microscopy, as well as dabbling in robust quantum control and quantum physics education research. Currently, she is a senior lecturer at the University of Bristol, where she is leading her own group, uh, which is uh, with research on the Bose-Einstein condensate, cold atoms, and Shaken-Lattice interferometry. And right now, she will give you a lecture on the introduction to cold atoms and Shaken-Lattice interferometry. So, Carrie, I'm happy to give you the floor.
All right, very good. What I'm going to try to do here, it's a bit suboptimal, but I can't get my tablet to connect here. So what I'm going to do is I'm going to share my screen. Now, what's going to come is basically an overview of atom cooling and trapping. This is not meant, so these are from old lecture notes, basically. You can see, not old, they're not that old. Um, but basically, what you can see is that this set of lecture notes that I'm about to cover sort of what does it mean for an atom to scatter light, and how can we use this for optical molasses, magneto-optical trapping, and then something known as dipole trapping. Uh, I will only very briefly cover real atoms and Bose-Einstein condensation, and that will probably happen after the coffee break. Um, but we'll also cover atoms and optical lattices. And then I will also discuss a little bit about this idea that Anton says that I invented. Really, it was sort of a co-idea between myself and the professor that I worked for in Gila. Um, and from there, I'm also going to place what I did in the context of what I like to call quantum control storytelling. So, what I want you to get out of this lecture is not necessarily an exhaustive idea of how we do atom trapping and cooling. I will point you to places where you can get an exhaustive idea. And I believe you'll be able to have access to these lecture notes once I'm done. But the point is that I want you to get out kind of an idea of how this is done. We'll talk even a little bit after the coffee break about how this is done experimentally because I am trained as an experimental physicist. Um, and so what we will be able to do is we will be able to set things up such that you have an idea of how one does atom trapping and cooling, but you'll have a place to go to learn more. And that's the whole point of all of this. Hopefully, this will be bolstered by the talks that you'll get later on in the week from some of my friends and my colleagues around the UK. And hopefully, you'll learn something. That's the whole point. Very good.
Oh, sorry to
Excellent.
interrupt you. May I ask you to zoom a little bit picture because it's a little bit small to make it larger. Oh, yes, it will be perfect. Yeah. Thank you very much.
Okay,
Thank you.
perfect.
Thank you very much.
Oh, no, no, thank you. And please, so I don't have a whole lot of time. So some of this I'm going to go rather quickly through. However, if you have questions, Anton knows how to get in touch with me. So feel free to write me an email or something along those lines. Very good. Excellent. So let's get started. The resources for learning cold atoms, kind of the most important one is in atomic physics in general. Christopher Foote wrote a book called Atomic Physics probably back sometime when I was still in high school or something like that. Um, and he's a professor at Oxford. He's basically a part of the furniture there. He's a lovely fella, does great physics. But his atomic physics textbook is fantastic. And so a lot of what I'm going to tell you comes out of Foot, starting mainly from chapter 9. And so in the first instance, I would say go there to learn. Daniel Steck also has an amazing set of quantum optics notes that basically is 1,000-page LaTeX document that tells you everything that you need to know. So what we're going to start with, however, so I'm going to try to keep this as large as possible while still being able to read it. So, okay, good. So what we're going to start with is the scattering force. And so if you've done any sort of undergraduate electricity and magnetism, we know that light carries energy, h bar omega, and momentum, which we'll call h bar k, where k is 2 pi over lambda, which is the wavelength of our light. Sometimes you see this written also as E equals P times C, and these are actually very much equivalent, as we can note here. Good. Apologies, I will try to turn that off. Good. Okay, so and as a result, because light carries energy and momentum, what you can actually think about is you can think about impinging on something. That something is going to be an atom, but impinging on something with a beam of light that carries a number of photons. But even a single photon hitting something will impart some energy or some momentum to that something. If we have a beam of light that has some cross-sectional area that we'll call A, then the radiation force is going to be the intensity of the light times that cross-sectional area divided by the speed of light c. And the radiation pressure then is force over area, so it's going to be this I over c. And so if you actually put numbers here, if we have a 1 watt laser beam, which is, I mean, that's a lot. That's something where you have to worry, quite a bit about laser safety, but it's not out of control. Then if we have a 1 watt laser beam, then the force from this 1 watt laser beam in about, I'm pretty sure in maybe a, millimeter square, something like that, you get forces that are on the order of about 10 to the minus 9 newtons, which is small, but it's not zero, right? That's the whole point. And actually, this is why comet tails point away from the sun, because of the radiation pressure from the sun. And so it can go around the sun, but that tail is always going to point away. Okay, great. Hold on 1 second. Can I turn all of this off? No, apparently not. It has to be a do not disturb setting. There we go. Perfect. Okay, now we will not be disturbed. Okay, so, but the whole idea is that when you have an atom that has some cross section to it, which we'll call sigma, is that this cross section is going to be so much different from the atom size. And this is something that I cannot go into detail here. So there are bits of this that you're going to have to take a bit on faith. They can be found in Foot. I can elaborate also. But the atom, if you think about an atom, the size of the atom is very, very small. However, the atom itself is a little antenna. And so the more resonant the light is with an allowed energy transition within an atom, the larger and larger and larger that atom is actually going to see. It's going to be so much larger than the size of the atom. And so what I have here is that this on resonance cross section of the atom as the antenna is so much larger than the atom size. It's orders of magnitude larger. Then actually on resonance, these radiation forces now become substantially non-negligible. So, 1 photon hitting an atom might not do much. 1 billion photons hitting an atom is going to do quite a bit. And so what an atom will do is it will see a laser and it will have a cross section that's Doppler shifted. And so that's what you see here. This cross section sigma is a function, that's what's in these parentheses, of the frequency of the light, omega. So that's then related to the energy in the light, h bar omega, minus k, which is the momentum here, and the velocity here of the atom, right? So that's what we're looking at. Is basically this is the Doppler shifted sigma, and then we have the intensity of the light divided by c. So this is just the same thing. This is an area and intensity divided by the speed of light. That's exactly the same thing that I've written here. So I'm trying to explain the terminology as I come about it. This would be a lot easier if I could write it out on my tablet. I do admit, because then I wouldn't have to, go back and forth between things. However, we deal with the technology that we have. Okay, so each absorbed photon, as I mentioned, is going to give the atom a kick. And the kick is going to be along the direction of the light. So if we've got the laser coming in and here's the atom that's moving opposite that laser, basically, if the atom is resonant, if it's absorbing photons from this laser, each of them is going to kick the atom in the direction opposite its motion, because it's going to get a momentum kick in the direction of the laser. And you can now kind of see how this could be used to slow something down. The analogy that I would give when I have, kids in my lab and they say, "Oh, I'm 8 years old. Explain atom cooling to me," which has happened more than once, one would say. Um, you think of it like wind. Like light is like wind to atoms, right? And so if you are out in a windstorm, for example, and you've got wind coming at you from all directions, you're not really going anywhere. It's not particularly pleasant. And so that's the type of scenario that we try to set up. And so basically what happens is that the atom will absorb a photon that will excite the atom up into the excited state, but it will also get a kick in the direction of the laser beam. But then it's going to emit that photon, right? Another idea is that atoms, the electrons in atoms are rather lazy. And so they're going to want to de-excite. They want to be in the lowest energy state that they can kind of stably hang out in. And so it will de-excite and it will emit a photon. And that photon will just get emitted in some random direction. Which, that momentum kick from that random direction, because the atom will emit the photon and the atom will get a kick in the opposite direction because momentum must be conserved. But that's going to be completely isotropic. If you do it once, yeah, that might matter. If you do it a billion times, well, that's a very good way of just getting something to average to zero, because there's no directionality dependence in where that atom, at least in free space, wants to emit that photon. This is just spontaneous emission. As a result, basically, there's going to be a net momentum transfer along the direction of our laser. And this will slow our atom down. Now, if the atom is, of course, moving with the laser and seeing absorption from the laser, that will then speed the atom up. So you can run this process in reverse, and we'll talk a little bit about how we can set things up so that we actually slow the atom down. So the idea is to set something up like what I've drawn here, and then the laser slows the atom down. Now, there's a scattering rate to this process, and this scattering rate depends on a number of things that I've gotten written here. So let me explain what all of these are. Again, to go into a lot of detail would not make a whole lot of sense with the time that I have. This is the type of thing that I cover in multiple hours typically. But this scattering rate is related to the basically the lifetime of the atom. That's what this gamma is. Basically, it goes from a ground state to an excited state, and then after some amount of time, it will then spontaneously emit. That amount of time is in this big gamma here. And then this P sub E is the probability that the atom is in the excited state, given the amount of light that is on it. So this omega here is basically proportional to the intensity. That's an omega. I know it doesn't look like an omega. I have funny handwriting. But this omega squared by 2, and then you have a delta squared plus omega squared by 2 plus gamma squared over 4. Again, the gamma is what's known as the line width of the atom, basically the lifetime of the excited state. And delta is basically how far are you from resonance, accounting for the Doppler shift, so we can see that there's the atom velocity in there. But then this big omega here is a rather complex term. This is known as what's a Rabi frequency, if you know the jargon. And the thing that you have to keep in mind is basically that this big omega is dependent on the intensity of the light. So this big omega, every time you see it, you can think of it as something that's proportional to the intensity of the light. And then we can actually set it in terms of this thing that we call the saturation intensity. And this is basically the intensity where we have about half of the atoms in the excited state and half of the atoms in the ground state. And that's basically given by the ratio of the intensity of the light to the line width, which makes sense, right? We want more light, we'll then promote more atoms to the excited state, but then we're also always fighting the line width that's trying to get the atoms back down to the ground state. And so the fact that this thing called the saturation intensity depends on these quantities, kind of the battle between excitation and de-excitation does tend to matter. Okay. And we can then put this into the form of a scattering force. Again, I'm glossing over a lot of the details here, which depends on all of these quantities. And we can look at basically what this looks like. You see, we've replaced all of these confusing omegas now with intensities. And our intensities as they relate to this so-called saturation intensity, which is basically, as I said, right? If you turn the intensity too far up above the saturation intensity, you're not going to make more atoms excited. Basically, population inversion doesn't like to happen in a two-level system, and that's the type of thing that we're considering here. And so basically, you can turn that intensity up higher and higher and higher and higher. You're still basically going to max out at about 50-50 atoms in the excited, atoms in the ground state. And there's a lot of really interesting quantum optics underlying this, but that's unfortunately, I can't give you an entire lecture course in all of this. I have to kind of just run through a few lecture notes. So please forgive me for the Swiss cheese. I promise you, I can point you to where these are filled in. Like I said, Christopher Foote's book is fantastic for this. But the scattering force, now you can see that if we take the limit that the intensity goes to infinity, then we get this sort of maximum force that we can impart on the atoms, which is basically the momentum of one photon kick, h bar k. And then since basically force is momentum by time, we now have the rate at which the atom then de-excites. And then, okay, there's a factor 2 here because, physics likes factors of 2. And so what we see then is that the maximum force that we can impose on the atom is going to be limited by the line width of the atom and then also the momentum that we can impart from one photon. And the momentum that we can impart.
Sorry for interruption. Can you a little bit zoom in because some people from the back rows, like it's yes. Very, they can't see the formulas. Oh, thank you very much.
Okay. Is this better?
Okay. Yeah, yeah. Yes. They showed it. It's better. Yeah.
Okay. Very good.
This is not the full picture.
Okay. I will have to go back. I'm trying to go back and forth as little as I can because I know that's kind of obnoxious. So, okay. But the whole idea is that this h bar k, this is basically limited by, you can't just choose this willy-nilly. This is limited by the resonance frequency of your atom. And you'll get an idea of what this means here in a bit. But what's actually going to happen here is that you're going to get, this isn't something you choose. Nature gives this to you. And nature also gives this to you, right? This is something that is completely outside of our control. And so we different atoms then have different maximum forces that we can impart. So this also gives a maximum acceleration. So we can just divide this by m, and now we get a maximum acceleration because F equals ma. And then we have this thing that we can write out as a recoil velocity. Basically, this thing here, this h bar k over m, is a recoil velocity because this is the momentum that one kick gives. And then, so that's a recoil momentum. But P equals mv, right? This is very classical physics. So now we have h bar k on m, and that's great because that's the recoil velocity. And you'll see this actually quite a bit. When you're trying to put light onto atoms, basically it's this recoil velocity that tells you how much these atoms are giving kicks. This recoil velocity will depend a bit on the atom and everything. It's typically going to be on the order of millimeters per second, give or take. So this isn't a lot of velocity, but actually that's not zero. That's actually, I would say, quite a bit. You do this 10 to the 9 times, you're probably going to slow something down quite a bit. Um, and then this gamma, basically 1 over gamma is a time scale that we now call tau. And so that's just another way of writing things. Okay, so here I've got some numbers. Chris Foot really loves sodium, so I put in a lot of sodium numbers. I really like rubidium. Rubidium is my favorite atom. And so basically, for sodium, you get a maximum acceleration that's 9 times 10 to the 5 meters per second squared. For rubidium, it's still on the order of 10 to the 5 meters per second squared. And you can see here that the recoil velocity is about 6 millimeters per second. And the point here, I have written right here, this is orders of magnitude greater than gravity. And we can control atoms. We can impart these accelerations on them that are massive compared to gravity, right? And so if you think about the accelerations, the maximum accelerations that the human body can actually withstand, right? It's a few G's, right? If you pull more than a few G's, you're going to, black out. If you pull more than a few of those, you're going to cease to exist rather quickly. We are imparting on our atoms orders of magnitude more of these. And I think that to me is just insane when you think about this. And that leads to the idea of optical molasses, because the idea is to cool all of the atoms in all 3 dimensions, right? So I mentioned this in 1 dimension, but of course, there's nothing keeping you from, and not even just 1 dimension, but sort of an atom seeing 1 laser beam coming from 1 direction. There's nothing saying that we can't do this from all dimensions. And that's awesome, because basically we could make all of these 6 lasers completely resonant with the atom so that the atom feels its maximum acceleration. But this actually only then works for atoms that have no velocity, basically. So it looks like this. We have an atom that has no velocity, and we've got lasers coming from all 6 Cartesian directions, right? So we have X, Y, and Z here. But we can only impart our maximum acceleration with our light being on resonance if the atom has 0 velocity. Well, what's the point of that? We want the atoms to slow down. That's the whole idea. Slower is colder, and colder is what we want. So the idea is actually now to think about what happens if the atoms don't have 0 velocity. If that is the case, we have to what we call detune our light from resonance. And so if we consider basically, and I'm going to zoom out just a little bit here. Let me try to zoom in. The zoom is quantized, so it doesn't like me. There we go. If we consider a 1D system with an atom moving to the left here, and it's seeing 2 laser beams that are detuned from resonance by some amount delta. This is red detuning. I basically have removed a frequency from the laser. A lower frequency has a lower, a lower frequency has a lower energy. And so basically this is what's called red detuning. So you can see here's the 2-level system of our atom. On resonance, the light would have some frequency, which I call omega naught, but I've detuned it from resonance by a little bit, this red detuning. If this were to be on the other side, basically if I swapped the signs of this delta, basically, then this would be what's known as blue detuning. The light that I'm imparting on the atom would have more energy than the atomic transition. I'm not going to talk a lot about that, but when that happens, usually you've got the atom will accelerate. That's not always the case. You can actually look up blue detuned magneto-optical tracks, and we're trying to make one in my lab now. But that is definitely that's a few levels above what I'm going to hit today. But it's extremely cool. And if you're interested, I can send you some papers. Some really lovely work went on at Imperial College London for that. So basically, this is the system that we're considering. And if we take into account the Doppler effect, what we can see is that, right, the atom is moving towards the left beam and away from the right beam. So the Doppler effect then shifts the left beam so that now it's in resonance. And the right beam is now shifted so that it's not in resonance, right? And that's what we want because the atom is moving towards the beam that's been shifted into resonance and away from the beam that's shifting it out of resonance. And we want the beam that is opposing the atom's velocity, that's moving against the atom, that's the one that we want to control. That's the one that we want to interact with the atom and slow it down. And we want the atom to basically ignore this beam on the right. Now, there are going to be other atoms in the sample that are going to be moving off to the right instead of off to the left. So we can't just get rid of that beam because then we're just got sort of one-sided cooling and that's not going to do us any favors. But for this particular atom, we care about it interacting with this beam. If we were to flip this, we would care about it interacting with this beam. So now basically this left beam has shifted into resonance and our atom is a massive antenna for this beam. And basically it will feel a force to the right that opposes its motion. And I write here that you can work out how this changes for blue detuned light, and you can. But basically, for a red detuned light, the atom is going to see that the beam that is counter-propagating with it is going to cause it to feel a force opposing its motion. And you can write down this molasses force. And, we do this basically. If you look at rubidium-87, this idea of this sort of this ratio of gamma over this K, which is 2 pi on lambda, gives you a velocity that's like in the ideas of, in the range of meters per second, right? This is rather fast, even, for a sprinter, I assume. Good luck going 5 meters per second. If this happens, you're not running, you're in an automobile or a plane or something. So this is many, many recoils, basically. And so basically, if my velocity is much less than this gamma over k, I can actually start to make approximations because I want to look at the scattering force of the beam on the left minus the scattering force of the beam on the right. That's what I'm doing. I'm looking at this molasses force. And I can make this approximation that as long as my atom velocity isn't so fast that the atom's basically sitting on a train, and you can work out that actually that's fairly reasonable, that you could do a Taylor expansion around these two beams. And so basically, as a function of this kV, and so you see that I've got my scattering force without the Doppler effect, and then the second term is the first linear term in the Taylor expansion that takes into account the Doppler effect. So that's one beam, and there's the second beam. And so you can look at this. And one thing to keep in mind is that, if you have a Boltzmann distribution of atoms at 300 Kelvin, the full width of path max there is about 400 meters per second. So we are actually only catching a fraction of atoms within this gamma over K. But it's enough, right? All you need is a few of these. If you have 10 billion atoms, 2% of that 10 billion atoms is still a billion atoms. And that's good because that's what we want to catch. Okay. And so then we get a molasses force that is basically proportional to the velocity by this term that I'll call alpha, which is related to how the force changes as we change the frequency of the light. And so we go through some of the maths. And hold on, let me just get back to I'll zoom back in here in a second. We can go through some of the maps, and I'm not going to go through it in a whole lot of detail because I'm running a bit out of time. But the idea looks like this. So let me zoom in on this so that both I can see it and you can see it. So this is basically figure 9.6 in foot. I want to, cite my sources where I can. And what you see is that this is the velocity of the atom here. And so what you can see is that the laser one, the beam on the left, that's moving from left to right, Here's the force that an atom with some velocity sees from the first laser. And so you see, okay, great, that's nice. And then it decays to zero for an atom with a velocity that's no longer opposing it. But that atom will then see the second laser. So basically, what I'm showing here is laser one is coming from left to right. If the atom is moving off to the left, then basically it's going to dominate what it will see. The force that it will feel will be dominated by laser one. And then in the other direction, basically an atom moving from left to right, yes, the other direction of the way it was moving previously is going to then see the laser that's moving from right to left. And so basically the laser will see, quote unquote, or the atom will see, quote unquote. The atoms don't see anything, they don't have eyes, but you get my point. Um, that the atom will basically see the laser that is counter-propagating it. You can then actually sum these contributions and you get this lovely curve that looks like this. There's no force at zero velocity, but we don't care. Those atoms are just going to hang out, and that's what we want. But what we see is that the force then opposes the direction of motion. Negative velocity, force in the positive direction. Positive velocity, force in the negative direction. And that's what we want. So that's what we get. On resonance, the forces from both beams cancel. So basically, if I don't detune my laser at all, if I have this delta equals zero, then that's great. The atom's resonant, but there's actually no slowing force. Basically, the forces will cancel for all velocities. The atom will see nothing, or it will feel no force. So we need that detuning. We need that red detuning to give us this lovely curve. And for blue detuning, this is going to be switched. And so if we want our atoms to slow down, we need our lasers to be slightly lower than the atomic transition. So there are some limits. This is actually what's known as Doppler cooling. There are some limits to Doppler cooling, and that's okay. So the limits to Doppler cooling, I'm not going to derive them now, but and they're in these notes, so you'll be able to see them, and they're also in foot. Basically, it's not just given by this picture that I painted you, albeit very quickly because I painted this picture in about 30 minutes, and this is something that nominally I would spend about an hour, if not more, on, and you would have had about 3 or 4 or maybe even 10 lectures beforehand to understand a lot of the sort of where these things like the big omega and the ISAT and whatnot come from. I'm trying to kind of paint a picture so that when you go back and you try to learn this in some more detail, you'll have a better understanding of what's going on. And later on, when I share some slides, which is admittedly going to be the more fun part of this, I think after the coffee break. So if you're bored to tears now, please bear with me for at least another half hour. And then we'll get to some slides and some fun part. But the idea is basically that the picture that I've painted you here is rather simple. You actually have to consider fluctuations to this force. And so that's what I've got written here. And I'm not going to go into it because we don't have time, but basically, if I can go scroll down to the punchline here, that our Doppler limit, where are we here? Basically, we can start to look at sort of the average velocity that these force fluctuations have on our atom, and we can start relating this to temperature via thermodynamics, if that makes sense. There's something in the chat. Okay. Yeah, somebody asked me a question directly about attendance. I don't actually know. So whoever asked the question about attendance, please ask one of the Ukrainian hosts. They would be happy to answer, I hope. But you can actually start relating this average velocity that arises because of these fluctuations to a temperature via thermodynamics, and you get a Doppler limit that we typically express in terms of temperature. And it's given here. I'm going to kind of just only going to bear, oops, I'm trying to zoom in a little bit. Sorry, guys in the back. You can do it. Oh, it doesn't like me. Yep. If you can't see this, please let me know. I'll try to zoom in further. But this Doppler temperature, which I call T sub D here, is related to the line width of the atom. So actually, the thing that controls, how much these fluctuations in force affect your atom is now actually given by the line width of the atom. In the jargon, what you'll often hear people talk about, especially when it comes to atomic clocks, are things like narrow line cooling and things like that. And the narrow line means that the line width is very small, so thus this quantity can also be made very small. This case of B here is Boltzmann's constant. And so basically you can relate this Doppler temperature to the line width of the atom. And so I've got some numbers here just to give you an idea of how cold we can get things. So for sodium, the Doppler temperature is about 240 microkelvin. This corresponds to a Doppler velocity of about half a meter per second. For rubidium-87, it's about 146 microkelvin. That's about what we can hope to do in my lab. And for cesium, because it's for cesium-133, which is another really, really commonly cooled atom, it's about 125 microkelvin. And so this is related to the line width of the atom that's really driving this. And so all of these are alkali metal atoms. It's basically a whole bunch of stuff and one electron on the outside, a whole bunch of filled shells, and then one electron. And the whole idea behind all of this is that that one electron is very, very, very easy to control. For a long time, people tried to trap and cool hydrogen, and they've had some success with it. And sorry, I need to turn on my computer charger so that my laptop doesn't die. There it goes. Now it's happy. And they thought, oh, well, hydrogen is such a simple atom that it would be really, really, really easy to cool. We know everything about hydrogen. And we do. We know quite a bit about hydrogen. It's one of the only, it is truly the only atom where we can actually make a lot of progress with pen and paper without having to sort of resort to various approximations. But it turns out hydrogen is very, very light, and that makes it very difficult to control. Lithium is sort of the next alkali metal, and it's also very light and very difficult to control. And people have made careers out of controlling lithium and doing all sorts of fun experiments with lithium, but it is very light and very difficult to control. Our friend sodium is a bit heavier. Rubidium and cesium are extremely heavy. These on a relative scale to things like hydrogen and lithium, and that makes them a lot easier to control. And actually, from a quantum sensing perspective, this is really, really useful because then these heavier atoms actually they're like big test masses that you can then use. Yeah, and so it makes things very, very interesting. There's a lot of work going on in cooling things like alkali metal atoms that now instead of one electron in an unfilled shell, there are two. And these are really useful for atomic clocks, which I'm sure you'll hear more about because they have these lovely narrow transitions. So you can go lower than these temperatures. You can go much lower than these temperatures with something known as subdoppler cooling. That is in Chris Foot's book. I'm not going to cover it because it takes quite a bit of time. However, what we can talk about is we can talk about magneto-optical trapping. And this is basically how do we trap these atoms? Such a trap is called the MOT. Some people call it an MOT. Usually you hear it is just called a MOT. Okay, so the idea behind a magneto-optical trap is that you're hitting atoms with near resonant light. Now, the atoms slow down, but I've just told you that they don't slow to zero. They slow down quite a bit. They get rather cold, right? Microkelvin's extremely cold. That's colder than a cryostat's going to get you. That's colder than basically anything that we can think about in our day-to-day life, right? These atoms are still really cold, but they're still moving. They're not going at zero velocity. And so the analogy that you can think about is that we've hit them with this laser wind. But what do you do when it's windy outside? You go behind a wall, right? You go inside, right? The atom kind of does the same thing. It's going to wander its way out of the laser beam eventually. So what we have to do is we have to provide the atom with a trap, with a way to kind of sit in, we have to tell it where we want it to be. And just laser beams aren't really going to do that. So what we do is we add a magnetic field. Now, okay, I'm going to zoom out just a little bit. Basically, the idea is that we trap the atoms by being clever with what I call light polarizations and magnetic fields. Now, okay, you can do it. Zoom out. Okay, I've zoomed out just a bit, or quite a bit actually. You can't see this, but you'll be able to unsee it here in a second. Basically, what I'm going to do is I'm going to talk a little bit about atomic physics. Now, an atom, just like if you've ever solved for the hydrogen atom, you know that basically the electron has a spin, it can be either spin up or spin down, right? So we'll call that S. S is the spin of the electron. Now, the electron, though, also has angular momentum, right? In sort of the Bohr model of the atom, right? The electron is orbiting the atom, and it's got some angular momentum as it goes about doing that, and we'll call that L. And we know that spin and angular momentum are both quantized, but the total angular momentum of the atom we will call J. So J here is the total angular momentum of the atom, or the electron rather, and J is L plus S. Cool? Everybody can see this? I hope. I don't know if I can make it much bigger, so I hope you can. Now, quantum mechanics is funny though, because the L plus S is the total angular momentum of the electron, but it can actually have a projection, especially when you have a magnetic field in your system. Then basically the angular momentum of the electron can either be aligned with the magnetic field, it can be anti-aligned with the magnetic field, or it can basically be somewhere in between, but only with integer jumps. And so we call that level of alignment with that magnetic field something called M sub J. And so we label our states with the J and M sub J. Now, if you know anything about atom trapping and cooling that's kind of beyond what I've tried to tell you about now, you've often heard of these as F and M sub F, and that's going one level deeper. So what I've described here is fine structure. F and M sub F go into hyperfine structure. If that last sentence made absolutely no sense, don't worry about it. Cool. So we have a fictitious atom here. I'm going to describe magneto-optical trapping with a very basic atom. We have a fictitious atom that has a ground state with J equals 0. So basically, our angular momentum and our spin are anti-aligned. Now, this is not exactly realistic, but bear with me here. And the excited state has J equals 1. So our M sub J, our projection can either be, along some sort of field, against some sort of field, basically +1 and -1 respectively, or just completely orthogonal to the field, which would be M sub J is 0. Now, our splitting with our magnetic field, basically this Zeeman effect that causes the energy levels of the atom to split with the magnetic field, is proportional to M sub J in the magnetic field of the magnitude of the magnetic field. And basically, the other little bit of atomic physics knowledge that you need to know is that linearly polarized light will drive transitions between states with the same M sub J, and circularly polarized light drives transitions between different M sub J states. So basically, if I have light that's horizontally or vertically polarized, it's not giving any angular momentum to my atom. So it can drive transitions from sort of my ground state, which is J equals 0, M sub J equals 0, to my excited state, J equals 1, M sub J equals 0. But if I have right-hand circular light, or say we'll call it sigma plus light, that can donate some of its angular momentum because my photon itself has angular momentum, then I can drive transitions between the 0, 0 JMJ state and the 1, 1 JM sub J state. Sigma minus light can go between 0, 0 and 1, -1. So if you don't know any atomic physics, you're probably like, what exactly are you talking about? Bear with me here. Okay, so what I then have is here's my two-level atom as a function of applied magnetic field here. So, and we'll discuss how we actually make this also a function of Z in a second. And so we're just looking along one dimension. So we try to zoom in so you can see it a little bit better. That's a little bit too big, sorry. Okay, so now my ground state has just m sub j equals 0, completely immune to magnetic field. It does not care because my energy splitting, which is what I've got here on my y-axis, is basically m sub j times b. But if m sub j is 0, it doesn't care. And it's, in reality, it's only 0 to first order, but we're only talking about first order anyway, if even that. Now, my m sub j is -1 state. You can see I have an energy that's decreasing as my magnetic field increases. My m sub j +1 state, I now have the opposite slope. And again, my m sub j 0 state just doesn't care. And it's these two states that change their slope, or rather that change their energy in the magnetic field, that's going to allow us to actually now, instead of just cooling the atoms, also trap them. So what I do is I set up two coils, one coil here at the top and one coil here at the bottom. And I run currents, which I've labeled with this curly I, in opposite directions. These are anti-Helmholtz coils. And they make a magnetic field that you can see I've kind of drawn here in blue. This is also out of Chris Foot's book. So if you, which I am pretty sure I can scare up a copy for folks who are curious. But basically what happens is that you've got this magnetic field gradient. And so as I move away, basically in the center of these coils, because these currents are opposing each other, this magnetic field is 0. But as I move away from the center of the coils, the magnitude of the magnetic field increases in all directions. There is a gradient of the magnetic field in all directions. But like I said, in the center, the magnetic field is 0. So now I set things up such that one polarization of light that I send in one direction is sigma plus, one polarization of light I send in the other direction is sigma minus. Basically, these are circular polarized light, which we can do very easily in the lab. So I have sigma minus coming from one direction, sigma plus from the other. So you see that every sigma minus pair has a sigma plus partner on the other side of the Cartesian axis. And what happens then is that the sigma minus light is going to drive transitions basically between the 0 and, sorry, this should be sigma plus, the 0 and the +1 transition. This guy here, which should be sigma minus, drives transitions between the 0 and the m sub j -1 transition. And all this does is allows us to have, as we move away from our center of our coils here at z equals 0, as I move away, the magnetic field magnitude is going to increase because I've got this gradient. And now not only do I have a Doppler force from the atoms moving in a certain direction, but I have a spatially dependent force. And my spatially dependent force is such that at the center of my coils, no force. Just like how at 0 velocity, we had no force on the atoms. What I want is I want atoms at the center of my coils with 0 velocity. But as they start to move away, the combination of their the Doppler effect, basically as a result of their velocity, and the magnetic field that these atoms are feeling, and the polarizations of the light that I apply, we set it up such that an atom moving in one direction, say along positive Z here, is only going to see this light because only this state is going to be resonant. The light that's counter-propagating is completely off-resonant because it can only address this state up here. But this is the state that we want. We've basically detuned from resonance. So this difference between this solid line here and this dashed line here is this delta. And so what I've basically set up, if you get nothing else out of what I'm about to tell you, is I've basically set something up that an atom moving along one dimension is only going to feel a force opposing it And then if something happens and it gets kicked so that it's moving the other way, it's only going to feel a force opposing it. And it's always going to want to go to the center of the coils. So as a result, we end up with a lovely little cloud of atoms that sits at the center of these coils. Um, and hopefully you'll get to see that on some lab tours. That would be really pretty fun. I might be able to scare up some pictures of the moths in my lab as well. So you can look at this mathematically and we can derive all of this, and it's lovely. The point is that we can capture billions of atoms, multiple billions of atoms, at a temperature that's about equal to the Doppler temperature here. And that's incredible. This sentence here is incredible. We can capture billions of atoms at microkelvin temperatures. And then what we can actually do is we can capture them in light-based traps, known as optical dipole traps. And we'll talk a little bit about that next time, after the coffee break. Um, but that I think is where I will stop for now, Anton. Is that okay? We can have a coffee break, and then
Yeah,
I'll have, I think, another hour to do to tell you a little bit more about things.
yes, of course. Maybe someone from the auditorium has questions.
Yeah, do we
Oh
have
yeah.
questions? Yeah, we have. Just a moment, we in the auditorium, the plate. Yeah.
Uh, Yes, thank you for this really important lecture. I had a question. So I've heard about cooling atoms with lasers before, and I always wondered about like when you pump laser beams to the system, you expect the energy to increase, and suddenly you have cooling. So what about the energy equation, perhaps? Where is
Yeah,
yeah?
I mean, this is a really good question. So the question is basically like, right, light beams carry energy. What's happening to all of this energy? Why isn't this heating things up, right? Like why is this cooling things down?
Yeah, exactly, exactly.
Yeah. And so like I guess your question is almost like how is this not just like completely violating entropy, right?
Yeah.
Yeah. So the answer to that is basically that this is um I mean that's a really good question. Let me see if I can reason my way through it. And then if the answer that I end up giving becomes like terribly confusing and I can't sort of, talk my way through it, then let me see if I can't hit it after the coffee break when I've had the chance to do a little bit of homework. Um, but the point being that like the simplest kind of experimentalist answer that I can give you is that the amount of energy that you need to generate the laser beams that you need, the light fields that you need, and how precise all of this needs to be is that like we'll never win. Like this isn't, the amount of energy that we're putting into the system versus how much we're cooling things down. Like it's basically I make the joke that this is a glorified refrigerator, and it is in the sense that like the lab actually becomes much warmer with all of the stuff that we need to run to run these lasers and to run the coils to do all of this. That like yeah, we're making a tiny fraction of the universe colder, but the rest of it is actually getting substantially hotter as a result. The reason why all of this works is basically because it's a delicate interplay between setting your laser at the absolute right frequency, right? Setting your magnetic field so that it's got the right gradient and all of these things, and setting your polarizations just so that you actually end up, taking a sample of atoms at about room temperature and cooling them down. But we really are only catching a fraction of the basically the atoms in the universe. In order to actually make this happen in real life, this gets back to when I briefly mentioned that like the Boltzmann distribution for atoms at 300 Kelvin, only like 2% of them are even cold, are even moving slowly enough that we could dream of catching this with our technique. Like we're catching an extraordinarily small fraction of the system and just sort of being able to remove the energy from that system through light. And the where that energy is going is it's actually being carried off by the light that's being spontaneously emitted by the atoms. So it's not that like that we're violating any sort of intrinsic physical principles here, but actually, and I'll see if I can't scare up some pictures shortly, but like these atoms glow like crazy. You can actually see them with your naked eye if we have, things working well enough in the experiment. And my rubidium atoms that are, my favorite, they glow red. Sodium glows yellow. Strontium, I think, is blue typically. And the reason why they glow is because these atoms are constantly emitting photons. We've just set up the system in our kind of clever hand wavy way, such that as these atoms emit photons, the atoms themselves become colder, but really the universe around them becomes somewhat large, substantially hotter. I hope that makes some sense.
Yeah, that makes a lot of sense. Thank you so much.
Cool.
So, yeah.
Thanks, it's a great background. And my question is why on the experiments mostly you use alkaline metals? Is it due to their simplicity or there's some another explanation?
Yeah. Alkali metals are the easiest because it's a filled shell and one electron. These atoms are hydrogenic in the sense that there's a whole bunch of stuff, a nucleus and a bunch of filled shells, but then there's one electron hanging out. And that electron is, for lack of a better term, very easy to talk to. Alkali metals typically have a very straightforward atomic energy structure that we can very easily measure via spectroscopy, but also that we understand very well theoretically. Alkali earth metals, sort of the next level up in complexity, that have two electrons, so they're very, they're helium-like, although that's a bit of a misnomer as well because helium is a noble gas, but they've got these two electrons. They can still be cooled, and people do. People cool and trap increasingly complex atoms, erbium, chromium. There's a periodic table of all the atoms that have been trapped and cooled, and there's some really random ones out there that have an incredibly complex electronic structure. But even the alkali earth atoms, their spectroscopy becomes substantially more difficult. There are many more states that are lying out there. When I start going through my slides, I'm going to talk a little bit about. I'm going to show you actually one of these energy level diagrams, so you see what a real atom looks like. And we even find that for our simple rubidium, which is a very easy atom to trap and cool, that we can't just do it with one laser. We need two. And it's because basically nature will not let us just keep treating the atom like a two-level system because it's not. It's going to then, the electron that we're trying to control will escape into other quantum states. And so we need additional lasers to basically coerce that electron out of these other states and into the ones that we care about. And so the more complicated your electronic energy structure gets, the more sort of other frequencies you need around to basically try to approximate as best as possible a two-level system. And there are people that trap and cool molecules that make magneto-optical traps and molecules, and they're just nuts. They need more lasers than I think I've ever seen in my life.
Thank you very much. Anton, maybe we have some questions online?
No.
Possibly.
Not
don't.
online. So, Keith, do we have questions? Oh, one more question, sorry, here from auditorium. There you go.
I have a question. Maybe I don't get about time of cooling. So while cooling using lasers, do we have problems that during cooling atom is still moving and we need to change target of lasers? And does it make a problem?
Mm-hmm. That is a really good question. For the simple model that I've presented here, the idea is that it captures a range of velocities. And so there's actually something I skip over it here, but I mentioned you can actually think of a capture velocity of atoms. And so this is kind of the maximum velocity that an atom can still have and then basically the laser plus magnetic field system can still be set up such that we can slow it down. This capture velocity is, like I said, typically on the order of a few meters per second. So we're still not catching the hottest atoms in a 300 Kelvin cloud, but we really don't care. Um, but there are ways that you can trick the system into either slowing your atom sample down, such that basically the atom sample that you start with has the velocity, this velocity distribution that you want. There are things you can basically slow atoms down with giant magnetic field coils they call Zeeman slowers, or you can actually also do this with light. There are other more complicated atom trapping or atom cooling schemes that actually ramp the frequency of the light in sort of a sawtooth pattern so that it goes up and then back down, and then up again, or the other way around, up and then down, or down and then up. And these sort of like sawtooth cooling methods are actually really, really useful for complicated atoms with complicated energy structure, or molecules or things like that. And so while basically the short answer, without going into too much detail, frankly, because I'm not an expert in these other types of cooling, is that what the model we have here is typically good enough. We don't usually have to change our laser frequency while we're cooling so that we, catch more and more atoms. Although when we want to make them even colder, the sub-Doppler cooling, we usually have to change things around a little bit. But if you have something that's more complicated, like you're trying to cool a molecule, then there are games that researchers play where they sort of fiddle with the laser frequency or the magnetic field or something along those lines, such that they can catch more and more atoms with a large or molecules or atoms with a larger range of velocities. I hope that made sense.
Yeah, thank you
Just
very
a,
much.
just a short comment that I think you will be able to experience the scariness of the cold molecules as we will be having a lecture on them on Thursday. So you will see this crazy structure and what they're doing there.
Fantastic. Who's giving that lecture, Ansel?
I think it's the postdoc of it's postdoc of Mike Tarbot.
Oh, fantastic. That's going to be an amazing talk.
Okay, thank you very much. And we have a short break. And I am rotating this guy.
Okay. I think is Carrie. Carrie, are you here? Okay.
Just wait.
Yeah, I'll write to her.
We have one question from online, yeah?
I think someone from the audience wanted to ask the question on the mic.
Okay, yeah, but just wait for speaker. Sorry. Yeah, so a little bit, and after that.
Yeah. Carrie's coming.
Yeah. Okay, good. But we have one more question from audience. Okay.
Yes, yeah, I remember.
All right.
Yeah, we have one more question from the local audience, if possible. Okay.
All right.
Okay. So
Very good.
just a moment. I'll get microphone.
Thank you. I wanted to ask, mostly clarify the question. The clarification question. Can you please once again describe how the magnetic trap is used? What does it do for our, what is purpose of it?
What is the purpose of what? Sorry?
Of the magnetic trap, which is used there.
Ah, yes. The magnetic trap now makes there be a spatially dependent force. So previously we had a force that was velocity dependent, and we still have that. But now, as a result of the magnetic trap, we have a force that is also dependent on space. And so as a result, we can tell the atoms to go to a specific point in space. Does that make sense? We set up a magnetic field gradient in all directions. And that then sets up basically a velocity and spatially dependent shift of the atom resonant energy.
The magnetic force in that case is have force on the atom, or we have some other lasers, and because of the splitting in the gradients of the magnetic field.
What the magnetic field does is it doesn't actually exert a force on the atoms necessarily, because the atom is a neutral particle. But yes, what it does is it can split the energy levels of the atom. And so what we want to set up a scenario where the laser is resonant with the atom only if the atom is moving away from the trap center with a certain velocity. And so if the trap center is in the middle of the screen and the atom is moving away, then I basically want the atom to feel a force this way. If the atom is moving this way, I want the atom to feel a force opposing it. And so what the magnetic field basically does is it shifts the resonant energy for the laser to interact with the atom as the atom moves farther and farther and farther away from the trap center. And so we set up a system such that with a combination of the shift that occurs due to the Doppler shift and a shift that occurs due to the magnetic field, is such that as the atom is moving away, at a certain point, it will come in resonance with this laser, and it will get kicked backwards towards the center of the trap. And then as it cools down, basically, and it slows down, then it will continue to feel a force towards the center of the trap until it's effectively slowed down to the Doppler limit.
So these lasers, they are pointed at not only at the center, but on a whole trap, if I understood correctly. And because of force.
Yeah, they overlap in the center of the coils.
Okay. Okay, thank you.
Yep.
Okay, thank you very much, Anton. And do we have one more question from online?
No, we don't.
Okay, so let's go with the next part.
Sounds good.
Thank you very much. Yeah.
Okay, this part at least has a lot more pictures and should be a lot easier to see. So if nothing else, there's that. Okay. All right. Great. So basically, this is a tutorial. This next sort of hour or so will be a tutorial on quantum optimal control and ultra-cold atomic sensors. And the idea is to kind of both go through a little bit of what we talked about in the past hour, but then also to tell you a little bit about how we control these systems in the lab. And the case that I'm going to use to tell you about how this works is going to be the work that I did during my PhD on atom interferometry with atoms in an optical lattice. And hopefully that makes sense to you at the end of this talk. So let's go for it. First, I'm going to tell you a bit about the necessary background. We'll talk a little bit about how we make and care for, okay, maybe we don't feed them, cold and ultra-cold atoms. And then I'll tell you a little bit about what it actually means to do what I call quantum optimal control, which is my favorite kind. And then, like I said, the case study. We'll talk about what I call a Shaken-Lattice interferometer, which was basically the title of my PhD thesis, was Shaken-Lattice interferometry. We'll talk about what atom interferometry is, basically practical quantum control. What I'm going to tell you is basically everything I did wrong during my PhD. Well, not everything. That list is way too long. That would be like a 5-hour talk. Um, but it can also be sort of what can you learn from my mistakes? Okay, so let's go into it. So what's in an atom? Well, we'll talk about our alkali metal atoms because those are my favorite, and they have one electron in an unfilled orbital. Very good. So what is the energy level structure of the single electron? And if you've learned it before, I'm going to use spectroscopic notation, which is basically N, which is the energy level of the atom, and then 2s plus 1, where S is the spin, L is the angular momentum, and J equals L plus S. So the ground state of rubidium is this 5-2s1/2 state. No angular momentum. The spin is 1/2 of the electron. 1/2 times 2 plus 1 is 2, and 0 plus 1/2 is 1/2. And then there's two excited states. This is the so-called D-line doublet. Every alkali metal atom has this. Basically, we increase the angular momentum of the atom by 1. So L goes from S, which is 0, to P, which is 1. We're using chemistry notation here, where it's S, P, D, F, G, H, Q, whatever, 12. Where S is 0, P is 1, D is 2, et cetera, et cetera. So hopefully you remember that from chemistry. And then basically the idea is that basically the electron and the angular momentum are either anti-aligned, so J is 1/2, 1/2 plus 1 is 1/2, or we have the angular momentum and the spin are aligned, which gives you 1/2 plus 1 is 3/2. Now, we have the D1 line, which is at 795 nanometers, or the D2 line, which is at 780 nanometers. And these are basically variations on red. Technically, it's infrared. Actually, in reality, if you shine these lasers on a white piece of paper, it's like they're trying really hard to be red. They're mostly failing, but they're trying really hard. So this is fine structure. And then we have hyperfine structure. And hyperfine structure has to take into account the fact that the atom has a nucleus. And the nucleus has a nuclear spin, which I believe is, let me do the math in my head. I believe that that's going to be 3/2. So basically, the F here is what's called I, which is the nuclear spin quantum number, plus J. And so 1/2 plus 3/2 in quantum mechanics notation is either 1 or 2, because that's how things add in quantum mechanics. So the ground state splits into these two hyperfine states. See, hyperfine structure. And our excited state, because we care mostly about the D2 line, then splits into 4. So 3/2 plus 3/2 can either be 0, 1, 2, or 3, because quantum mechanics says so. And the splitting here is actually kind of interesting. This is about 6.8 gigahertz. This is in the microwave. But here we've got about 267 megahertz. Still in the microwave, but there's actually two very different pieces of equipment that we use to hit this guy versus this guy. And then we've got our Zeeman splitting. So as I add a magnetic field, these two levels will then split further, and these M sub F states, which are degenerate at 0 magnetic field, will start to split apart. So how do we cool an atom down? Well, the idea behind all of the quantum sensing that I'm going to tell you about is that if you get bosonic atoms cold enough, where cold enough is about 100 nanokelvin, then basically the de Broglie wavelength of these atoms is going to be on the order of the interparticle spacing. And interestingly enough, if you run the numbers, the de Broglie wavelength is actually going to be on the order of about 500 nanometers. These atoms start to have a wavelength that's very similar to visible light, which I find very interesting. This is known as a Bose-Einstein condensate, or BEC. And so what we do is we start with atoms that are basically bouncing around at room temperature. So 10 to the 2 Kelvin. And these are basically atoms as billiard balls. Every cold atom physicist on the planet has a slide like this. So you'll probably see a number of slides like this. Hopefully this is the first in the summer school, which means I get to be the first, which I'm very happy about. And then we use the magneto-optical trap, right? We have our two coils with currents running in opposite directions. We have all of our laser beams, which intersect here at the center, like I mentioned. and there is some overlap, and these beams are usually fairly large, a centimeter or two typically in diameter. Now, this is a magneto-optical trap or a MOT. And so the atoms stop really behaving like billiard balls, but they still have de Broglie wavelengths that are quite small. And then what we can do is we can cool them further to Bose-Einstein condensation, where basically what you see is that these atoms really do start to overlap. And they stop really looking like distinguishable, atoms that we can identify and address, even though I guess they never really were. But they actually start to collapse down into one single quantum wave function. And so this comes out of the original science paper where rubidium BEC was first reported. And so what you see is that the thermal atoms that are in the MOT start to become colder and colder and colder. And this peak that you see is really the signature of a Bose-Einstein condensate. And the way we do this, I don't have a whole lot of time to get into the detail of. However, what you do is you take a MOT and you start selectively removing the hottest atoms from the cloud. And then the atoms will rethermalize and they'll get colder and colder and colder. And you keep removing the hot atoms and the cold ones stay. This is how we don't violate entropy. We have to be very clever about making sure that we remove the hot ones and keep the cold ones. And then it takes quite a bit of energy actually to remove those hot ones. So we're never really, ruining our fundamental laws of physics. It's like the cup of tea that I've got here. Actually, this is a little bit of miso soup. And so what's happening is, as I blow on it, the hot steam is leaving. This cup of, hot beverage that I have here is okay. It's blurred, but it's cooling down. Very similar process with the BEC. It's actually called evaporative cooling. And these atoms actually become mutually coherent. They become phase coherent. They become phase stable. They're a lot like the photons in a laser. And that's really cool because I have my atom laser with my rather deranged looking atoms here. One of the interesting things about them is because they're massive, they're slower and they're heavier, which makes them easier to control. And they're excellent sensors, right? If I shoot a laser beam across the room, it had better not sag under gravity. Because if it does, something's horribly wrong. But my atom laser better sag under gravity. And that sag allows me to measure gravity. And that's why atoms make incredible sensors. And so you talk about quantum technologies, atom-based quantum technologies are amazing for sensing because every atom is the same. And they all are going to react to external fields like forces of gravity and motion, acceleration, rotation, magnetic fields, electric fields. They're all going to act identically to the influence of these things. So if I have a billion atoms and I measure their, how they react to gravity, I'm going to get very good counting statistics. Okay, so how do we do this? Well, there's a couple of ways that we can trap atoms. One is in magnetic fields. And magnetic trapping relies on the atom's magnetic dipole moment interacting with the magnetic field. And that's very cool. So basically the split in energy is going to be given by the atom's magnetic dipole moment mu dotted into the magnetic field, and then there's a minus sign out. Now, if mu is aligned with the magnetic field, if mu and B are aligned, then basically the atom has a lower energy and a higher field, right? Because of this minus sign out here. It's called the high field seeking state. Vice versa, if mu is anti-aligned, this is a low field seeking state. And so what you've got here is we've got this same splitting diagram, right? Here are my two ground states of my rubidium atom, and they're split by about 6.8 gigahertz. This one that's lowering its energy in a higher magnetic field, this high field seeking state, is sort of this M sub F equals 1 state, and then these -2 and -1 states here. These states here that increase their energy in increasing magnetic fields, this 1 state, this 1 -1 state rather, or this 2 MF equals 2, or F equals 2 MF equals 1 state, or F equals 2 MF equals 2 state. These states are low field seekers. We like low field seekers And the reason why we like low field seekers is that we can make magnetic field minima. But there's a theorem out there that tells you that you cannot make static magnetic field maxima except at the boundaries of your system. And so high field seeking states are notoriously difficult to work with. I play almost exclusively with low field seekers. Cool. So we can make magnetic field minima, say via our Helmholtz coils, and you can see here's the magnetic field gradient map that you see. It's 0 here in the center, and it increases as you move away. And what we want to do is avoid zeros of magnetic fields, because then all of this energy degeneracy here, all these states that are so nicely split, all that splitting goes away, and basically the atom doesn't know what M sub f states it's in, and it gets all sorts of confused, and this can cause losses due to spin flips and these types of things. Cool. So you can make traps with coils, like I've shown, current carrying wires. So these are atom chips. These are really fun. This is actually the chip that I used for my PhD work. Basically, there's a whole bunch of gold wires patterned on this chip, and we ran currents through them. We ran current through this one here, marked in yellow, and this one marked in white. And at the intersection of these two wires, we made a BEC. It was awesome. It was really great. Good. Now, we can also use permanent magnets. This comes out of Peter Hannaford's group at Swinburne, which is in Australia, outside of Melbourne. And they make these are permanent magnets arranged in a lattice pattern. So they make permanent magnet lattices. It's really cool. Seemed like a nightmare to work with for me personally, but they're also really cool. We can also trap atoms with light. And this is really interesting. This is kind of the bread and butter of what I try to do now. Light induces a dipole moment in an atom. So basically, the dipole moment here is proportional to the applied magnetic field. And it's an induced dipole moment, which means in the absence of light, the atom, you say, hey, atom, what's your dipole moment? It goes, what? No. But in the presence of light, now it has this dipole moment. And this gives rise to a force and a potential. Sorry, I'm getting experimental results sent to me, which I'm excited about, but that's for later. And so the potential here is basically proportional to the intensity of the light. So actually, you can ignore kind of this F equals minus grad U. Just look at the U. The U is proportional to basically this polarizability of the atom, this alpha, which is proportional to the frequency of the light that we shine on it and the intensity of the light. And so for red detuned light, actually, this potential then becomes attractive. It's like if I take my atoms that have 780 nanometer resonance frequency, and I shine, say, an 800 nanometer light beam onto them, they're going to see that as like a tractor beam for atoms. They get sucked into this intensity maximum, and that's what I've got here. And I'm going to sneeze. Pardon me. All right, very good. And so we see here that the atoms sit in the intensity maximum of this light that I've focused down. So this is just a Gaussian laser beam that I focus down, and the atoms sit at the intensity maximum. The depth here is going to be proportional to the intensity divided by the detuning. And actually the scattering rate, which is bad, this is basically the rate at which the atoms will scatter the photons in the light field that they're in, is going to be proportional to the intensity of the light divided by its detuning squared. And what this actually means is that we want a lot of power from a laser that's far detuned from resonance. Great. So the optical lattice then is really fun. It's an egg carton for atoms. So I can take a laser and I can reflect it back on itself to create a sinusoidally varying potential that looks something like this. I take a laser beam and I allow it to hit a mirror and come right back onto itself. Maxwell's equations force at a metal mirror us to have a node right here. So I know that there's no light there, but it sets up this sinusoidally varying interference potential. This is the light interfering with itself. And the spacing between these different maxima is given by half of my lattice wavelength. And the depth of my lattice, which I typically express in actually a recoil energy. So you remember the recoil momentum, the recoil velocity that I talked about last time. You can actually set that up as an energy just by using 1/2 mv squared. And so I usually express the depth of my lattice in this quantity called recoil. where this is basically h bar squared k squared on 2m. And then this s here is a scaling factor. So if I turn my laser power up, my lattice becomes deeper. If I turn it down, my lattice becomes more shallow. And so that's what that S parameter is telling me. And it works in up to 3 dimensions. In 2D, we get a series of tubes. And in 3D, we get a cube with the whole, where the vertices are where the atoms like to play. But everything I'm going to tell you about today, we're just going to work in 1 dimension just because it's easier. But this does get a lot more fun when you work in multiple. So how do we describe the atom wave function in the lattice? Well, there's 2 equivalent ways that you can actually do it, right? So I've got a sinusoidal potential, and I've got an atom in that sinusoidal potential, and my Hamiltonian takes the form of p squared over 2m plus my b0 over 2 cosine of 2kx, these types of things, right? This is the potential that I put into my system, rather. And I can either solve this using Bloch's theorem, which if you've had any solid state physics, you're probably a lot better at than I am. And these are neutral atoms, remember, not electrons, so we don't have to include Coulomb's potential here. But the idea is that the atoms become delocalized in position. And this actually gives rise to band structure. And so you can set up systems like this, where this is the dispersion curve of my atoms. This is basically their momentum, or their, this is related to their velocity, and then the energy. And so you see, you get this incredible band structure. So this is the lowest energy band. The blue dotted line is the next highest, and then next, and then next. And so what you can see here is that you get this incredible band structure, and this is actually repeating on itself because of the periodicity of the lattice. And the wave function of the lattice, this is actually the red one here that we see. So this dashed line is just our lattice. The red curve that you see is just the ground band at basically quasi-momentum or momentum 0. And then this blue one is at a momentum of h bar k. And so what you can see is that it's a very periodic structure with the periodicity that's related to the lattice periodicity. And this is really cool because actually these become quantized in momentum. So the Fourier transform of our position space wave function gives us our momentum space wave function. And if we've got something that's nice and periodic in position space, it's going to be quantized in momentum space. Basically, we've got different components of the periodicity that correspond to what's actually going on here. And it's actually that quantized momentum that is what I'm going to play with in my sensor. We can actually also sum up all of these Bloch bands, all of these Bloch functions within a given band, and we can localize our atoms to a single lattice site. This usually works with a very deep lattice. And a lot of people play with this. If you've ever heard of like Bose-Hubbard type models, a lot of these are based on Wannier functions and this idea of atoms being localized. So deeper lattices mean more localized atoms, but the game that I'm going to play is with actually rather shallow lattices and atoms that are delocalized. So I care about their momentum quantization, not the fact that they can be in one lattice site. These aren't eggs in an egg carton. They're a lot more like broken eggs in an egg carton. Cool. So that's how we get lattices. Now let me tell you a little bit about quantum control. I'm going to go rather quickly through this bit, but hopefully you'll have the slides available afterwards so that you can remind yourself what I was trying to talk about. Good. So quantum control. It's the control of quantum systems. There's 2 types, coherent control and optimal control. Coherent control solves the whole problem. It's like the Feynman path integral approach, where you're sitting there and you're going, I want every other process to destructively interfere except the one that I care about, and I'm going to do all of the maths and I'm going to solve it, and it's going to be great. And it works. It's very much physics focused. Optimal control rather just says, okay, we're going to optimize the process, and we're going to do so, we know the physics, but actually writing out, the actual maths of what's going on becomes rather, well, not straightforward, for lack of a better term. And so via this optimization, we then find something that works, and then from there we can start to look at the physics of the problem. which for a lot of physicists, especially theoretical physicists, seems kind of backwards. And to be perfectly honest, it is, but it's one way that works. So what we're going to talk about is actually this way of optimizing a quantum process and extracting physical insights, but then actually using physical insights to make that optimization of the quantum process better. So you can control state transfer. Basically, you can say, I have some initial state and some final state. So that if you don't know Bra-Ket notation, this is just a vector denoting a state. If you do know Bra-Ket notation, awesome. And so I have a state that I start with that I usually know and a state that I want to finish in. And I just say, I want to know the process that goes from psi A to psi B. You can you can control unitary operations. I can optimize a U that will act on any state in the same way. If you know anything about quantum computing, this would be like gate optimization. Good. You can choose between two ways of doing this. You can optimize a model or you can optimize an experiment. Good. And you can optimize for speed, fast, sensitive, not sensitive, any sorts of things. So if you have the state transfer problem, basically, the idea is that you have some Hamiltonian that you can control in some way. You need some knob to turn. This isn't going to be a static problem. You have something that some knob that you're going to turn. Maybe it's the lattice depth. Maybe it's the lattice phase. Maybe it's, so your laser power or where your mirror sits or something along those lines. How can you go from some initial state, some desired state in some time t? Well, you can evolve your state, which you can do mathematically here. So this t is time ordering. And it's basically just a way of doing this integral in a way that doesn't make you want to cry. So you have some unitary evolution between this state and some final state. You can do open quantum system generalization of all of this. I am not going to touch that today. And so usually your Hamiltonian, not always, and actually in the case that we're going to discuss today, it can't be written like this, but you can write your Hamiltonian as some bare Hamiltonian plus some other Hamiltonian terms that you can turn on or off with your controls. So, good. Now, what we have is we also have different landscapes and different algorithms. I'm going to go very quickly through all of this. But basically, what you have is you have a set of mountains that describe where you want to be. And so you can either have a few optimal or you can have many optima. You can have very smooth, easy landscape. This is like hiking through a nice rolling set of fields. Or you can have a rugged landscape where every single one of these mountains is a pain to climb and, who are you to try to climb it? You can have a number of mountains that all have kind of the same height. These are all going to give you equally good answers. Or you only have one good mountain and a whole bunch of really not good hills, right? So basically, when you look at these solutions, kind of the lighter the color, the better your solution is. You're somewhere here in this search space. Here would be a 2-parameter search space. We usually have a lot more than 2 parameters. And so basically, every time we guess, we sort of plop ourselves somewhere in this landscape. We call that a seed. And then we can have all of these different ways of looking at our landscape. It has been said that actually if you have no constraints, you have no local maxima, just one global maximum. I tend to ignore this because experimentally I never have no constraints. What they're saying is you can always turn your laser power up to infinity. That's not a thing I can do. If I turn it up too high, it breaks. There are different algorithms that you can use. You can actually use local algorithms that just climb the nearest mountain. They get to the top and they say, this is the solution that I have found. It's probably amazing. I'll get to this question here in a second. It can get to this, this mountaintop is amazing. I know of no other mountain. A global optimizer can sit there and it can go, well, I'm going to climb these, 8 or 10 mountains and I'm going to see which one is best. So there's the question of what does an attractor mean? An attractor is basically an optimum. So when I mention of this local optimizer, where you're climbing up basically a mountain and you get to the top of the mountain, you say, I'm here, I'm at the top. You have now experienced an attractor. I can then take my local optimizer and I can start it in a different place. Say I start it, instead of being on the mountain on the left here, I start it on the mountain on the right. It's going to climb up to the top of that mountain. And basically, no matter where I start my local optimizer, it's either going to end up at the top of this mountain or the top of this mountain, or it might end in a very, very flat place, in which case it also gets confused. But if I've got many attractors, I've got many possible optima. And so my optimizer can sit there and it can try to climb up any of these different mountains. So an attractor is like, it's like an optimum. Oftentimes, actually, when I describe this, I don't describe it in terms of a maximization problem, but a minimization problem. So you sort of invert these pictures. So instead of going up to the top of mountains, you go down to the bottom of valleys. And then the idea of it being an attractor, like a marble rolling downhill, is a lot easier to kind of digest. I hope that makes sense. Okay, cool. You can also define an algorithm's ability to explore versus exploit, which is like if you have an algorithm and it only wants to hang out on one mountain versus being able to look at other mountains. So gradient-based methods are typically local. They basically you plop them somewhere on the mountain, it takes the derivative and it says that way's up, and that's the direction it goes. A gradient-free method actually doesn't do any derivative calculation. But these are all lots of details that I just want to kind of expose you to so you understand a little bit more when you go try to learn. And if you have questions about this afterward, feel free to reach out. Now, you always need a functional that tells you how good you're doing. So basically, you have to decompose this entire complex problem into one number that you can minimize or maximize. And you always are going to lose information, right? Anytime you're trying to decompose something extraordinarily complex into one number, you're going to lose something. But the idea is that you can have example functionals. And in this example functional, which looks kind of gross, but it's not all that bad, I'm going to take you through it. I have a control, a final state, and a desired state. So my control U, I have my final state and my desired state. Basically, this first term just tells me how good I'm doing. Say I'm trying to minimize my functional. So whereas previously we were trying to climb mountains, now we're trying to duck into valleys. And for the rest of this talk, I'm going to talk about valleys, I'm pretty sure. This first term basically looks at the overlap between my final state and my desired state, subtracts it from 1 because I'm trying to minimize, and basically the lower this number, the happier I am. I'm also trying to minimize these guys as well. Basically, this guy here is trying to minimize the energy of my control. I square my control and I integrate it over all time. I can also try to minimize basically large variations in my control. I take the derivative of my control, I square it, again, because then integration is easier. I integrate it over all time. Basically, the larger my u of t or my u of t squared is, the larger my magnitude of my u of t is, the larger this is going to be, the larger or the more my u of t changes, the larger this guy is going to be. And then this basically is a way that I can sort of work my way out of any sort of, forbidden subspace. Say I have a state phi k that's not a good state to be. I want to avoid being in that state. I can penalize for it. I can have as many terms as I want, but the addition of each of these terms makes life more and more and more complicated. So I try to keep things as simple as possible. And the weights, these lambdas, which can be dependent on time, but they don't have to be, determine the relative importance of each term. If I'm doing state transfer, I probably want this lambda not to be rather large. But if I really, really, really want to make sure that my control doesn't change quickly, maybe lambda b is large. Or maybe I want my control to actually be as small as possible. Then lambda a can be large. So basically, that I can balance these weights with respect to each other. And you can actually do multiple state-to-state transfers with the same control field, and you can sum multiple fidelity terms. Although if you're doing this too much, I would say just work on unitary optimization. This functional does pick a final time t, but you don't have to do that. The fastest possible transfer does define a quantum speed limit, but quantum speed limits are extremely difficult to prove outside of more than the simplest problem. So, You can do unitary optimization. You can define something like a fidelity of transfer. So if I look here, this guy here, sort of the overlap squared of my two states, this is a fidelity. 1 minus my fidelity is an infidelity. So how do I define something similar for unitary optimization? I can actually look at my desired unitary. Sorry, this should be a capital D. I can actually multiply it with the final unitary that I get, trace over it, divide by the dimensionality of my system. And so that's something like a fidelity. Take 1 minus that if I want to minimize, and look at that. There we are. So that's just very quick. I'm leaving this in here because unitary optimization is interesting. It's not what I've done so far, but it is actually something that we're looking at now. Good. So how do you do quantum control? If none of what I just talked about, because I went rather quickly, made any sense, what can I teach you? Well, the first thing you need to know is what is your problem? If you don't know what your problem is, you don't know how to solve it. So what type of problem is it? State transport, unitary optimization? What are your controls? What knobs can you turn? They're usually, if they're virtual knobs, they usually correspond to something real in an experiment somewhere. And if they're real knobs, then they hopefully very much also concern something real. Are they laser powers, magnetic fields, electric fields, phases? Are they, what are they? What do they correspond to? Couplings between qubits? Are they, couplings between atoms? What are they? And what are their limits? This is important. You can't turn a laser up to infinity, right? So, that's what you need to know. And understand what information can you get out of your system, right? You got to talk yesterday on quantum measurement and quantum estimation theory, I believe. What can you measure? With my atoms, it's actually very, very difficult for me to get relative phases between different states, but I can get amplitudes really easily. All right, there's another question. What will happen when the particle uses the coherency? I am not going to address this now. I might address this after the talk. Sorry. So sorry, that was one of the questions in the chat. Understand what information you can get out of your system. What can you measure? It's really important. What information can you get easily? What information can you not get easily? What information can you get in a simulation that you can't get in an experiment? Understand this. This is really important. If you don't listen to anything else I talk about, this is important. And then finally, what algorithm will you use? Will it be global, local? Do you require gradients? No gradients? Sometimes in experiments, gradients are really difficult to do because you typically have to do gradients numerically, which means you have to run an experiment many, many times to try to estimate a gradient. Now, if your experiment's very noisy or it's very slow, that can then make your algorithm very, it can basically make it so that your algorithm doesn't work as well, or that your optimization takes forever. Optimization is not good for anything if it takes you 6 years to optimize, right? Like at that point, just go solve the problem. And then this is the really crucial bit. Is there anything you can make use of in the physics of your system that will simplify your problem? So this last question is the crux of what I'm going to talk about. So good. I'm doing all right on time. So hopefully in the next half hour, I can tell you a little bit about kind of my story of how I got all of this to work by getting it to not work to start. Good. So what I was trying to do for my PhD, and actually what we're working on now, I finished my PhD in 2018, and now that I run my own research group, this is exactly what we're doing again because it's interesting, it's cool, and somebody gave me funding to look at it. Which those are the three things I care about: interesting, cool, and somebody's paying me to look at it. Good. So, what is quantum sensing? Quantum sensing is basically using an inherently quantum device to sense a quantity. And atom interferometry is just one option for building a quantum sensor. It's the one that we're going to talk about, and you're going to hear talks from people like Mike Kolinsky, Mike has done atom interferometry for a long time, and he has done some amazing work. So I'm going to leave it to him to tell you a little bit more about what he does and how he does it. But it is just one option for building a quantum sensor. And atoms are just one option for building a quantum sensor. You can use ions, nitrogen vacancy centers. You can use superconductors. There's all sorts of different ways that you can build a quantum sensor. You can use light. So atom interferometry typically measures motion. And by motion, I mean acceleration or rotation. And cold atom systems have also been used to sense magnetic fields, say via the Faraday effect, where the polarization of light rotates if it interacts with atoms that basically have been exposed to a magnetic field. And yeah, like I said, there are other things that make excellent sensors. It's not just atoms. And the applications here range from inertial navigation. So like if you have a submarine, for example, you can't use GPS. The water gets in the way. And if you run a submarine aground in a hostile country, that's a problem, right? And so what you need to be able to know is where is your submarine as you're navigating around. And so this becomes a very, very interesting and sort of geopolitically fraught question. But you also have other applications that aren't perhaps so, intrinsically violent, like medical imaging. You can use atom sensors to look at, people's hearts and people's brains, and this is incredible work. And you can also look at tests of fundamental physics, right? They used an interferometer to detect gravity waves. That was awesome. They used quantum light in the interferometer to detect gravity waves, which is incredible. So quantum sensing is not only is it one of the most of quantum technology, but I think it's one of the most useful. And you could say, oh, but quantum computing. I said, yeah, very good. Build me a fault-tolerant quantum computer, and let me show you these guys, down the street in Nottingham who have a 3D printed helmet that measures brain waves with atoms, because they have that now. So, okay, that's, quantum sensing is incredible. Okay, so let's talk a little bit about interferometry. Traditional interferometry, you've got a source of waves, a couple of beam splitters, a couple of mirrors, and you shoot your source of waves at your beam splitter, splits it apart, then propagates to the mirrors, reflects off the mirrors, propagates again, recombines on a beam splitter, and what comes out you detect on a photodetector, and you get fringes. If you've never done this in a lab, if you're a theorist, you probably hate it. If you're an experimentalist like me, we used to race to see who could align this thing the fastest. But yes, I was a giant nerd. I continue to be a giant nerd. But these things are really great. An atom interferometer is great fun, because instead of my laser, I can replace it with my atoms, right? So these are my deranged atoms from a bit earlier in the talk. And what we can actually look at is something known as the Sagnac effect for rotation sensing. And I can have the length of the area that's enclosed by my system and the width of the area that's enclosed by my system. So area is L times W. And I have something that's rotating at some rate big omega. So this is no longer a Rabi frequency or anything. This is just the rotation rate. And so I have my area, which is length times width. And then the phase difference that these two different arms pick up is related to the rotation rate in the area, the wavelength of my wave, and the speed of my wave. So let's plug numbers in for light versus atoms. Light moves at the speed of itself. Atoms have some mass and some thermal de Broglie wavelength, which is related to their mass, and their velocity, which is related to their temperature. I can plug these numbers in, and all else being equal, this atom system can be 11 orders of magnitude more sensitive than my light system. Now, it's very difficult for everything to be equal. For light systems, my area can be huge. For atom systems, it's very difficult. But this whole idea, this 11 orders of magnitude as an idea, is very, very interesting. A lot of these questions I can't really answer right now. They're not they're addressable perhaps at the end of the talk for the person that's writing questions in the chat. So how do we describe this atom wave function in a lattice, right? What I told you, right? So the type of atom interferometer that I hope that you'll hear about when you hear my Kolinsky talk will be different than the type of atom interferometer that I'm going to tell you about today. The type of atom interferometer that they're building in Birmingham is a lot more advanced. That technology is a lot more advanced. They're doing incredible stuff. So when he gives a talk, don't be like, so Carrie gave us a talk a couple of days ago. I want you to say why hers is, also awful and yours is awesome. Please don't make us compare. But his is a lot more well advanced. Mine, though, it's young, it's hip, it's cool. So remember, I've got my block functions. And so we've got our band structure and our lovely delocalized atoms. This, like I said, gives rise to quantized momentum states. So my atoms at zero quasi-momentum, because they're not moving. Remember, I've spent a lot of time and effort and money to make my atoms as slow and as cold as possible. So they're not moving right now. And so they have these quantized momentum, where my momentum state is quantized in units of h bar k. So here we have 0 h bar k, and then 2 h bar k, and then here's 4, 6, 8, so on and so forth. So I have my 0 momentum state, this is in the lowest band here. And then in the first band, you see that there aren't that many atoms in the 0 state, but there's a couple out here in the plus minus 2, some out here in plus minus 4, so on and so forth. And it's this quantized momentum state that's really the crux of what I'm trying to do. So that's what we did. We built the Shaken-Lattice interferometer. We trapped our atoms in an optical lattice potential, except now we could control the phase. So the lattice was actually able to move back and forth, and that's why we called it a Shaken-Lattice, because by controlling this phase, the lattice moved. And that was fairly straightforward, pretty easy to do experimentally. And we used this shaking to control the momentum state of the atoms. And so the atoms were delocalized. Our model was limited to basically momenta quantized in units of 2h bar k. Looked like that from the last slide. And starting from atoms in the ground state of the lattice potential, which was this one here on the left for band 0, I could build splitting. Come on, you can do it. Propagation, reflection, reverse propagation, and recombination back into the ground state. So what you have here, this is one axis, say the x-axis, going from left to right, and then going up, down, you have time. So basically, I've enclosed an area in space-time. This is in one dimension. So this isn't a rotation sensor. It's just an accelerometer, but it's an interesting accelerometer. So how did we do this? Well, we started with our initial state and the objective function, which is convergence into a desired state. And we tried to build the phi of t that did what we wanted. And I tried this with pen and paper. It's extremely difficult with pen and paper. It's the type of problem that beyond the very simplest of cases, you need a computer to solve it. And so then I used an optimization algorithm to try to teach the lattice how to control the atoms. And instead of just trying to find a phi of t, I actually just tried to find the frequencies that mattered. So I had a whole bunch of Fourier amplitudes, and then I would basically find the Fourier transform of my phi of t. I would then take that Fourier transform so that I would get the time wave function, or the time shaking function, and then I would apply it. So basically it looked like this. There's my system, my atoms are blue, my lattice is red. I have a computer, and I say, I want a split state. I want half of my atoms in one momentum state, half of my atoms in the other. The computer thinks up some shaking function. We shake the system, and well, it doesn't give us what we want. So we reject that shaking function. Computer goes away and it thinks about it a little bit, comes up with another phi of t. We then do the experiment again, and everybody's happy. So that's what we did. Okay, it didn't work after the second iteration. Didn't usually work after the 200th either. But we got it working occasionally. And once the shaking function was known, it was fixed. We knew how to sort of build our interferometer, and then we could see how the system responded to a signal. So if we go back to our recipe, the idea was that I knew everything. I could define my problem. I could determine what controls I had. I knew what I wanted to change. I just wanted to change this phase, this shaking phase. I knew what information I could get. It was very, very easy for me to measure the population in each of these momentum states. It was very difficult for me to measure the phase between them, but it was very easy to measure the population. I knew what algorithm I could use. I solved this actually on a computer before I solved it in the experiment. But what I didn't think about was this last bit. Was there anything I could make use of to simplify the problem? We all good? Cool. So I had to be smart. I mean, that's kind of the whole point of, doing any of this, but I had to be smarter. So I had a control that was just the sum of a bunch of cosine terms for some random frequencies within about 100 kilohertz bandwidth. And I had some set of, amplitudes. This was just the sum of a bunch of cosines. Really basic Fourier theory. And the thing is that I used random frequencies. But these split states, if you look at them, right, as I go higher and higher in the band, if I wanted to say split and have half of my atoms in one momentum state and half of the atoms in another momentum state with equal and opposite momentum, all I needed to do was look. Band 1 was plus minus 2h bar k. Band 3, plus minus 4. Band 4 was the same as plus minus 3, but actually these have a phase difference between them. So band 3, these have a phase difference of 0. Band 4, they have a phase difference of pi. Band 5, again, was plus minus 6. 6 was the same, but again, with that phase difference. 7 was plus minus 8. And the farther and farther I split, actually, the more sensitive my interferometer is. So I was really interested in these types of things. But I didn't think about this physics for quite some time. So instead of picking random frequencies, once we started to look at the physics of the problem, actually look at what we wanted versus what physics was telling us we could get, we could actually drive these band-to-band transitions using phase modulation. So if you look all the way back here, this is the downside of having a whole bunch of animations on your slides. If we go all the way back here, what I wanted to drive the transition directly, the frequency that corresponded to the difference between red and blue, and red and other red, and red and blue up here, or maybe blue and red and blue up here. Like these, if I actually, instead of just randomly choosing frequencies, if I shook the lattice at the frequency corresponding to these energy differences, I was going to win. And you know what? I did. That's exactly what happened. All right, so we go through, we're happy. And so that's what we did. We drove transitions between these states. And we had to look at the parity of the states, and that's okay, and I'll kind of gloss over that. But we found that actually, like, we didn't need to do any optimization. We could just split with one frequency. And actually, I could obtain splitting within about 10%. This is my error relative to the state that I wanted as a function of kind of the amplitude of, how much I was shaking this thing. There were a number of different frequencies that worked. And it was just, I didn't have to optimize a thing. This was just looking at the physics. It was great. So this was actually going from 0 to the first band transition. And then this was half the frequency of going from the 0 to 2 band transition. So this is actually single and two. I use photon here. It's more of a phonon, if you know what that the difference is there. And so the whole idea was that we were able to get this to work by virtue of understanding the physics intrinsic in the system. And so instead, we just started looking at these band transitions, these ones that I pointed out on the previous slide, and we improved the optimization a lot. We were able to optimize this. This was on a computer, not in the experiment, but we were able to optimize very quickly to within like 1% error, which for us was very, very good. In the experiment, we only got about 10% error for various reasons. And so we calculated basically how much the states, these different band transitions overlap. We found out that a whole bunch of them didn't really talk. These were these kind of black dots here. But these colored boxes We looked at them and we didn't care about diagonals because I don't care about going from 0 to 0 or 1 to 1. I care about going from 0 to 2 or 1 to 3 or 2 to 4. And so we picked all of these 1, 2, 3, 4, 5. These guys are the same. It's symmetric. And then here I had 1, 2, 3, 4, 5, 6. So instead of going from a whole random, almost infinite space to 11 frequencies, that's all I did. And I did it because I looked at the physics of the system. And the more you dig into this, all of a sudden physics was telling me that I didn't need to care about anything else. I just cared about these 11 things. So we optimized just using these frequencies. And we were really quick. So this is 2H bar K splitting. And I know I just told you that we could do this with one frequency, but we had 20 iterations, which wasn't too hard to do on the computer. And then black, I had the old way of just sort of randomly picking stuff, throwing stuff at the wall and seeing what stuff. And then in red, I have the new way of understanding the physics of my system. The open points are sort of the average of all of the different points I was trying to optimize. I was using a genetic algorithm for those that are interested, which is not the best way to do it, but it's what I used. And then the filled bits where that was the best solution I got. And so I was able to get about 10% error in the old way after 20 iterations. I was able to get 1% error in one iteration, the new way. Okay, fine, but that one's easy. What about 4H bar K? Well, it turns out, okay, it takes about 10 iterations to get below 1%, but one really well. And the old way of doing things hasn't budged. It has to look for these frequencies that matter. 6H bar K was even better. Maybe it took us 25 iterations to get down below 1%, but that was something I could do in the experiment. It took a while, but I could do it. But the old way of doing things wouldn't even touch it. And so I was figuring out ways to make my system more and more and more and more sensitive, quicker, smarter, by understanding the physics of the problem. And that's the most important part of doing quantum control. And that's the most important part, I think, of doing any type of physics, experimental, theoretical, so on, is understanding the crux of the problem and understanding what matters and what doesn't. And so this is actually called the curse of high dimensionality. It's actually it's rather similar to the concept of a barren plateau in quantum computing, if you understand that, or rather quantum. I believe it's quantum machine learning. And we're able to do substantially better. Sorry. There's the question of what do the black points represent? The black points were the old way of doing. So, and then the red points were the new way of doing things. So basically, the old way of doing things was just sort of randomly picking a bunch of frequencies and seeing what worked. The new way of doing things was like, yes, we know what we care about. Let's only stick with what we care about. So that's the whole point. Yeah, so the broad takeaways. This has been a lot. I've hit you with a fire hose. I don't expect you to have understood every little aspect about how you trap and cool atoms. Every little aspect about what it means to be an atom in an optical lattice. Although if you're interested in this sort of thing and you want to understand it in more detail, the maths is not that terrible, and I can point you in the right direction. But atom trapping and cooling is awesome. Atomic physics is great. There are other types of physics, that don't use atoms. You have superconductors and NV centers and these types of things. But atoms are really fun. So please take that away. Atoms are fun. But you should, okay. That takeaway is basically your theory model can be good, but experiments, typically you need to work within experiments if you want something to actually work, because your theory model might not catch everything. I don't talk too much about that in this talk. Optimal control methods are varied. The best one for my problem is probably not going to be the best one for your problem, which might not be the best one for another problem. So it depends on the problem at hand. And the other thing is avoid that curse of high dimensionality. Think about it. What physics can you apply to a problem? I present this in the context of quantum control because I really like quantum control, and I think that it's a fun tool to have in your toolbox as a physicist. It doesn't solve everything. You're not like, with quantum control, I can now do everything. Like, Don't think that just because all you have is a hammer, everything looks like a nail. Like, use it as one of many tools, but it's a fun tool to have. But in all cases, think about the physics that you can apply to a problem. That's really important. So that's all I've got. Now I've got the black screen of I have no more slides. So thank you very much. Now I guess I can ask questions.
Thank you very much. I believe we have questions. Yeah, that's a local audience. Yeah, one moment, please.
Thank you for your beautiful talk. And my question is, you showed us a simple optical interferometer and said you could change light for atoms. But could you explain in this case what would be splitter and mirror and another linear optical level?
Yes. No, it's a very, very good question. These types of atom optics, as they're called. So I do it in a slightly different way. So actually, when Michael Holinsky, for example, talks, he's going to discuss a completely different way of doing these optics. But the way I do it is, actually, this is easier if I just do this. I use the lattice. So basically, what I can do is I control the momentum state of my atom, right? So if I want to make a mirror, one way to make a mirror is I can have, two clouds of atoms that are moving with equal and opposite momentum. If I want to turn them around, what I have to do is I have to switch their momentum states. And I can actually do that by modulating the lattice. And then the atoms that are moving this way turn around and they go like this. The atoms that are moving this way turn around and they go like this. Now I say like, oh, I can just do that. It's easy. It's not actually. Like the devil lies in the details, right? It's actually a very difficult problem to solve. It's I think it's nigh impossible with pen and paper. If you can solve it with pen and paper, please come talk to me. Let's write an actual paper. But the idea is that this idea of controlling the momentum states by modulating the lattice, that's how we can implement these types of atom optics. So the splitter, again, was taking atoms with mostly zero momentum and then modulating them so that half of them had a momentum moving one way and half of them had the momentum moving the other way. So that's how we did it in our system. Other ways, other means of doing atom optics usually rely on the interaction of atoms with light, but that's not always the case. There are groups, for example, at the University of Arizona, back in like the early 2000s, would actually fire atoms at actual gratings, and then the atoms would diffract off of the gratings, just like light would diffract off of the grating. So, just an example.
Thank you very much. More questions? Maybe from online? Or we have here offline also from local audience. Yeah.
Thank you very much for the talk. I have two questions. And the first one is on this very slide. Maybe I didn't get, but in this lattice potential, this is phase 5, which you can control. Can you please explain what is this physically?
What this phase phi is. So, a cosine, if I change cosine and I make it a cosine, of x plus phi or x plus pi, I basically flip my cosine over. If I make it x plus pi over 2, my cosine becomes a sine, right? As I change my phi, my lattice moves back and forth. If I continuously change my phi, I can actually make my lattice just run, where the momentum states, or rather the nodes and antinodes, rather, not momentum states, will just move continuously. So that's what that phi actually corresponds to. Now, if we go back to the slide where I discussed making a lattice in the first place, this one, where I have here. So here's my lattice and my mirror. And like I mentioned sort of offhand, that Maxwell's equations force us to have a node here. What I can actually do to change the phi is I can move my mirror back and forth. And if I do so quickly enough, that's okay. That'll shake the lattice. Now, that's not actually what I do in the experiment because it's actually quite difficult to move a mirror back and forth at enough speed. But what I can do is I can have one beam coming this way, one laser beam with the same wavelength coming this way, and they'll interfere, right? That's all that's happening to make a lattice. Now, if I change the phase of this laser beam relative to this laser beam, which is not all that hard to do, there are various different ways optically that I can do it. What will actually happen is that the interference pattern of these two interfering beams will shift back and forth. Does that make sense?
Okay. Anton, maybe we have something online?
Yes, we do. There were two questions. What will happen when the particles lose the coherent states before they interact with matter?
So this question, I don't quite understand what you're getting at here. Now one thing I did mention, I'm going to try to answer what I think you mean. What I did mention is that the states were phase coherent, right? That was the whole point of the BEC, is that these atoms they were more like photons in a laser than they were like anything else. If they lose that coherence, then yeah, we have nothing. The atoms need to maintain that coherence. So what will happen? Well, nothing good, basically. And part of the challenge of quantum and quantum technologies as a whole is actually keeping this phase coherent. Does that make sense?
Anton?
Yes, we have more questions. So again, from the same person, can we see or measure the quantum sensing phenomena at room temperature?
There are the best examples I can give of that are that the atom magnetometers that we use actually now there's a company that makes them. It's called QSpin. They use hot atom vapor, and so that actually they're not just at room temperature; they're quite a bit above room temperature. So yes, you can. That is a way of doing quantum sensing. There is an argument from one of my postdocs who's working on this that that's not actually quantum sensing, but atoms are quantum, so it's quantum sensing. And then the next question.
Yeah, I can just read it aloud.
Yeah, I can do it. Can you break down the underlying motivation between localization and delocalization of the wave function? Let me get to this first, and then I can try to mention the Sanyek a little bit, although I'm not sure I can do a great job with that. Now, the localization, that one lives here. So let me go here, and I'm just going to put the whole slide up on the screen. Okay, now, there is something really interesting goes on. Actually, I'm going to show you a slide that I wasn't originally intending to show you. However, I have lost my mouse. Apologies. Give me 1 second. PowerPoint is just being a bit painful. There we go. This one here is the one that I will show you. So I didn't want to show this slide because this was the Bose-Hubbard Hamiltonian. But one thing that it will do is I can show you two different examples. What I want you to look at is actually these pictures. Don't worry about anything else on this slide. These pictures show and actually I'll take this off. This shows a shallow lattice, and this shows a very deep lattice. Now, with the deep lattice, the atoms are ordered like eggs in an egg carton. They are localized to a given lattice site. Now, one thing that Heisenberg tells us is that the more we know about the atom's position, the less we know about the momentum. So actually, because these atoms are very nicely localized in the lattice, in position, their momentum state washes out almost completely. Now, these superfluid atoms, which again, the idea of what it means to be a superfluid versus a Mott insulator is something that I don't really want to talk about, because that's a whole other lecture in itself, is that this is more a shallow lattice. So these atoms, that's the periodic wave function that I was showing you. right? That's not one atom per lattice site. And actually, the idea of the atoms being here, in a given lattice site is also kind of a waffly one. So these atoms, this is more the sort of delocalization. The atoms aren't just in one site, they're kind of spread throughout the entire lattice. Now, because they're delocalized in position, the less we know about their position, the more we know about their momentum. And so that's what you see here. This is actually looking at the momentum space wave function of these atoms. For this very deep lattice, this sort of 20 recoils depth lattice, the momentum is very smeared out. I can't tell you anything about the momentum with a whole lot of precision. However, this S equals 3 case where the lattice is very shallow and the atoms are very delocalized in position, the momentum states are very, very obvious, very easy to see. It looks like a diffraction pattern because that's almost exactly what's going on. I hope that makes sense. Now, the Sagnac effect, the best way that I can think about it, there's basically another question here on, can you elaborate on the Sagnac effect a bit? What I can do is I can kind of take us back to, I
Just a
believe,
small comment because we're gonna have a specific lecture on the Sagnac effect on Thursday. So, but yeah, sure.
yeah, I mean, all it really means in this context, or all I'll really talk about in this context, is because the Sagnac effect, this is deep, right? You're having an entire lecture on it. But what I would think about the relative phase that gets picked up between this arm and this arm, going down and back. Sorry, let me hide the chat window. Down and back, down and back, right? Now, if this system is rotating, you can see that basically the path length that's traveled by this top arm that goes across and down, or this bottom arm that goes down and then across, is going to be different, right? Because basically this encloses a circular area in space. And so that phase difference that gets picked up as the system rotates, that's what you're measuring with the Sagnac effect.
Okay, thank you. Anton, more questions from online?
No, I think that's all from online members. Maybe
Yeah,
someone
and
else
what
from the
about
audio.
offline? Yeah, we do have some questions. Just a moment.
Another question. Indeed, you said that you have found the optimal like control and parameter phrase, which depends on time. I wonder if have you built actually some kind of functional which you were talking about to optimize somehow the signal? What was the form of it? What have you optimized in this case?
Yep. My functional was actually in the experiment, my functional was very, very simple. Because I knew, so what I did here, so this was kind of my gross functional. In the experiment, what I knew is that the experiment was going to do this bit for me, this third term, right? This third term penalizes for high bandwidth controls. And I knew that the experiment, it just wouldn't work above a certain band. So that did it for me. I did it myself. I said, I'm not going to go any faster than 100 kilohertz. So I designed my system in that way. I then ignored this last bit because I didn't really care about, there were no states that were bad. I wasn't trying to avoid anything. I didn't really care. That was fine. So I ignored this last term. And then I set this idea of kind of controlling how fast my control was. I just did that because I knew how fast my experiment was. And so I didn't need this one. And then the second term with the amplitude of my control, I said, you know what? I don't care. As long as it works, I don't care. Now, if I'm going to explore this again in the future, which I am, we might care a little bit more about this. So actually, my functional was very simple. It was only this part. I had a time t that I picked. I limited myself in terms of how fast my control was just completely out of the box. I didn't need that in my functional. All I cared about was my fidelity. So that was the functional that I used. Does that make sense? It was very simple.
Just so cool that you have eliminated all the other terms. Thank you.
Yeah, thank you very much. More questions? Maybe not. Okay, let's set our speaker again.
I can. Oh.
Thank you very much. Thank you very much for your very nice lecture today. I believe students.
Thank you for your attention.
Yeah, learned a lot today, and thank you again. Have a nice